All right, hello and welcome, guys. I thought I would go over yesterday's assignment, and since we're not going to be able to whiteboard it like we would normally do, make a few comments about it and talk about how we can take what we did with the bar graphs and build it into a more formal problem-solving methodology. And so, as you did the assignment, you probably ran into a couple that just weren't very convenient to use the bar graphs for. Number 3, for instance, which is on the screen. You had to draw 60 some boxes if you're going to use the ratio of 5m to 1m, and so you need those 5 mass boxes vertically and then 12 velocity boxes horizontally. Maybe you found a way to shortcut that or draw fewer boxes, but the most straightforward and simplest way had you end up having to draw and count a lot to answer the problem. And then you get to 4, and it's just not doesn't really work at all because it's not nice multiples. And so we end up with 7.5 velocity of 7.5. And how do you draw half a box? So we're going to take a look at this, and I'm going to show how we can use this basic bar graph as a guide to a more formal problem-solving process. And so here's, I guess that's number 4 again, but a different way. This time, instead of drawing all the boxes, I'm just drawing one big bar. And the width of that bar is my velocity. So you can see in my picture, my before picture, I have 12 meters per second to the right. So I have a bar that's going to the right. I've labeled the width of that 12 meters per second because that's the velocity. And that's the convention we already had with the bar graphs, that width was velocity. The mass is 1.25 kilograms. And we'd already said we were going to do vertical on the vertical direction, one box for every mass multiple, or somehow represent more mass with a taller box. So I've just labeled the height now 1.25. Now I can multiply those two things together to get an area of that box. And that represents this quantity, mass times velocity, which we've said that's what has to be conserved. This quantity of mass times velocity, which so far we haven't given a name to. We just know the quantity of mass times velocity has to be the same before and after this event, as long as we have an isolated system. So what I know then is on my other box, I know the height is 2 kilograms. The two cars are stuck together and has a total mass of 2 kilograms. I don't know the final velocity or the velocity after this collision. So I just label it V after. And so then I can see that 12 times 1.25, the area of the first box, has to equal the area of the after box, which I'm just going to set up an equation as 2V after. And then I will solve that for V after and get 7.5 meters per second. And so this is our basic system that we can do. For every box that you have, you're going to have an M times V. And so in a simple case like this, my total MV before equals my total MV after. That's always going to be the case. These bar graphs help us fill in those MVs. MV does have a technical name. It's momentum. So momentum is RM times V. Not super important right now whether we have a name for it or not, but there is the name, and we'll move on. And I do want to look at number 6 because number 6 was another one that didn't work out to easy numbers. And so I'll just show you how this method works for this one, which is especially nice because it has a little bit more going on. It has negative direction, it has two things moving in different directions and things like that. So it's a useful one to look at. So you can see in the before, the car is moving 10 meters per second to the right. So I have a bar going to the right. And I labeled the width of that bar 10 meters per second. The car had a mass of 0.25 kilograms. So I've labeled the height of the bar 0.25. After the collision, car A is now moving to the left. So now it has a bar going to the left. I've made it shorter or not as wide, narrower, because it's slower. And I've labeled that 5 meters per second, but it's still the same height. Car B, I know, is more massive, so I've made a taller bar. I don't actually know what its velocity is. I just kind of drew a random width and labeled it V after. And so you can see my before is still very simple like it was before. It's my MV of that one box. So backing up a second, we have 3 boxes total. So you know I'm going to have 3 MVs total. On the before, there's only 1 box, so it's 10 times 0.25, the velocity times the mass. And then it's going to equal, we're going to add the 2 boxes together on the right side. But pay attention, car A is going to the left. So that actually is going to become negative, or you can think of it as subtracting that momentum, that MV, because it is in the negative direction. So I'm subtracting 5 times 0.25, and then I'm adding the other box, which had a velocity unknown, V, labeled V final in the equation, but V after on the picture, and a mass of 0.75. You do the algebra, solve that out, you get the 1.66 meters per second. So hopefully this makes sense, and you can use this problem-solving process to solve more complicated problems without nice, easy ratios. And I would definitely, when you get into momentum problems, I definitely encourage draw the before picture, draw the after picture, draw your bar graphs, and then use the bar graphs to write that equation. Hopefully it'll just have one unknown, and it will be fairly simple algebra from there. All right, thanks for watching, and talk to you. See you when we get back from this snow break.